So we're still discussing the effect of recycle on the mass balance in reactive systems, and we discussed in the previous example uh, some important things, and we saw that we can improve the overall conversion of the process greatly by doing this recycle. So this is a very important thing, and we saw that the flow rate was high, and this was expected because we have a lot of unreacted species in stream 3. And one thing that we mentioned, which is an important point, is that there is a product which is propylene that's fed to the reactor, while the fresh feed is free from propylene. And this propylene that entered the reactor is a result of the separation, the separator is not 100% efficient, so there are some propylene that is returned back to the reactor. So this is a very, very common case, and it's very common also in case of inerts, and this is what I'm going to be covering in this video. So inerts in reactive system, this term, it means that species that is part of the feed to the reactor or to the process, but it doesn't participate in any reaction. It doesn't necessarily mean that it's an inert gas. It's not helium, not neon, not argon. It can be, but it's more general than this. It's anything that doesn't react in the conditions of reaction. It can be nitrogen, it can be carbon dioxide, it can be water vapor, it can be anything. As long as it's not reacting, we consider it as inert. Okay, and since it's not participating in any reaction, it's not going to be, or the number of moles of this inert is not going to be changing. So the number of moles entering the reactor is equal to the number of moles exiting the reactor. So this is simply what it means. So if we have inert and in the feed to the reactor, and that the system or this process contains or includes a recycle stream, then it's very, very common that the inert concentration will increase due to the recycling of the unreacted species. So this is a very, very big and a common problem, and we will discuss it in an example. And I hope this example will make it very clear when it comes to the demonstration of the problem and the solution that we take to solve this problem. So let's look at this case here, where we have ethylene reacting with benzene to produce ethyl benzene, and this is the feed. It's 1000 moles ethylene, 1000 moles benzene, and it contains 500 moles of inerts. And the feed is fed to the reactor. We have the conversion is 70% of ethylene in the reactor. So it's a decent conversion. It's not very high, but it's decent conversion. The effluent from the reactor is fed to a separator, this is the effluent. Of course, it contains the ethylene, benzene that are not reacted, the ethyl benzene, which is the product, and the inerts that are not affected by the reactor. And we have some relations here about the effluent from the reactor and the effluents from the separator. We are told that the separator is designed so that the top product, which is stream number 3, contains 90% of ethylene, 80% of benzene, 5% of ethyl benzene, and 70% of the inerts in the feed to the separator. So we have a ratio between each one of these species, or the flow rate of each one of these species in stream 2 and stream 3. So what we are going to do is we are going to do the mass balance calculations for this system under in two cases. The first is the process as is, so we don't recycle anything, and after recycling the unreacted species. And if you look at the numbers, you would see that the ethylene and benzene most of the ethylene and benzene are recovered in the top product. So if we recycle, then this is the stream that will be recycled, which is stream number 3. So if we do the degrees of freedom analysis, then we see that the reactor should be solvable, and after the reactor we can solve the separator. And my goal is not to solve this problem and find numbers. I already posted the numbers. You can check the numbers yourself. or do the calculations yourself, I mean. But what I want to look at now is the numbers. So from the results that we have, of course, the conversion is 70% of ethylene, and the stoichiometric coefficients is 1:1, so they are fed with the same ratio. So we have 300 moles of ethylene and benzene that are not reacted. 700 are consumed in both, producing 700 moles of ethyl benzene, and the inerts is the same. And these are the flow rates that are produced from the separator in the top and in the bottom streams. And you'd see this is rich in ethyl benzene, this is rich in ethylene and benzene, and inerts, of course. So if we solve the same problem with the recycle, we are recycling this stream. Now we add one more unit, which is the mixer, and there is one extra stream, which is the feed to the reactor. And then the feed to the reactor is then producing the stream that is fed to a separator, and then we have the recycled stream. So this is the flow sheet, and this is the flow sheet after solving it with the same given information, with the same conversion, the single pass conversion. In this case, it's the conversion in the reactor, and with the recycled stream, or I mean the ratios between the components in stream 3 and stream 4 now. You would see here that the conversion of ethylene that was here 70%, it's now the feed is 1000, the product is 41. So it's I think it's 96% or something. So it's little less than 96. It's 95.9%. So the conversion is greatly improved, and you would see here, and this is worth noticing, that the flow rate of this stream is less than the flow rate of this stream. This is 2500, and the recycled stream is, I think it's going to be around 1600 or 1500, something around this. I haven't calculated, but this is what we see. And this confirms what I was mentioning in the previous video, that as the conversion or the single pass conversion increases, the recycle flow rate would be less. And this is what we see here. Last time it was the recycle was 9 times the fresh feed. Now it is less than the fresh feed. So it's just a side note. Okay, so these are the results that we will get. Okay, and of course, because we have steady state conditions and this stream is not a product anymore, then the number of moles of inert in the feed will be the same as the number of moles of inert in the product. This is very expected. So let's compare the results that we got from the two cases. This is the results without recycle. These are the results with recycle. And here I want to, I don't know if the numbers are clear, but I want to mention something here. So first, the numbers that the flow rates are in black, and the green numbers between brackets are the mole fractions. This is what I'm having here. So if you look at the numbers, there are some very, very important observations that we will see here. So one thing that you would be thinking of is the product. So it seems that the product is much, the number of moles of ethyl benzene that are produced are much more than before. It's I think it's 1.5 times, which is a very, very good thing, because we have now more ethyl benzene that's produced. And this is what we expect when we have a recycled stream. But the other point, which is the important point actually, the very important point, is regarding these two streams. Okay, so I'll zoom in again just to have a closer look on these two streams. So this is the stream that is fed to the reactor. In the previous case, it's the fresh feed. In this case, it is the mixed feed, which is the recycled stream plus the fresh feed. If you look at the numbers, you would notice very, very big change in the numbers, both in the flow rates and in the compositions. And what you would notice, of course, the number of moles of ethylene and benzene are higher, which is expected because we are providing more ethylene and benzene to the reactor. But the more important thing is the inerts. You'd see that the inerts is 1,666 moles, while it was here only 500. To make it more comparable for the numbers, because this number might be larger, but it might not represent a lot if we compare it to the rest of the components. So I want to be focusing more on the concentrations. So the concentration of inerts in the feed stream to the reactor is now 39%. So it's a very very big part of the recycle, or I mean of the feed to the reactor, is inerts, and this leads to the dilution of the main reactants, which are the ethylene and benzene. So here it was 40% ethylene, 40% benzene. Now it is 32% and 27%. It's very, very important for you to know. Of course, this is something you'd know later in reaction engineering, that the rate of reaction, which is the speed of reaction, is proportional to the concentrations. So if you have low concentrations, like in this case of ethylene and benzene, then this will reduce the speed of reaction or the rate of reaction, which will consequently lead to need of larger reactor, so that the components stay in the reactor for longer time to achieve the same conversion, and this will lead to more energy consumption, and this is and more capital cost. So it's a lot of expenses that would be resulting from this. And as you see, the inerts is a big part of the feed stream. It's the major part of the feed stream is the inerts, and it's not doing anything. It's just entering and exiting the reactor without reacting. It's also no, it's not actually doing anything. It's doing a negative thing, which is reducing the speed of reaction. So the advantage that we achieved by recycling the unreacted components is now leading to another problem, which is reducing the rate of reaction due to the high concentration of inerts in the recycle stream. And this is something you would see here as well. And for the recycle stream here that we see, we have 2/3 of the stream is inerts. This is a big part of the stream. So we are putting or paying money for a pump and for operating this pump or a compressor, whatever the unit that we have, to pump material that is not useful, and actually it's now getting very very harmful for the process. So this is a big problem that we face here, and this is the accumulation of inerts in the reactor. So the recycle leads to the accumulation of inerts in the reactor, and this reduces the rate of reaction and the rate of production of desired product, and it puts more load on the recycling equipment. So we have to find a solution to this problem, and this solution is a very very simple solution, but it's a very effective solution as well. This solution is what we call a purge stream. So the purge stream is that we don't recycle the whole stream. We will sacrifice part of the ethylene and benzene, and we will get rid of some of the unreacted or the inerts here. Okay, so the goal of this splitter is to find a place for reducing the concentration of the inerts in this loop. So instead of having all the inerts returning back and accumulating in this loop, part of them are going to be purged in this stream, and of course we are losing some of ethylene benzene, but this is more economic than recycling the whole stream. So this is what we call a purge stream. We have a splitter here, and the amount split, it depends on the economics of the process. We can we can purge 10%, 20%, 30%, depending on the process economics, which would be more profitable. Okay, so if we purge, like in this case, we purge 30% of the recycle stream, and I want to compare again the numbers. So these are the same stream after in case of purging and without purging. So here we have the purge stream, and look at the numbers. Okay, the numbers are very very important to look at. So in this stream we have, now it was 32 and 27%, now it is 36 and 34%. So it's getting better. Of course it's not as high as it used to be in the fresh feed, because you will have more inerts in the recycle in the fresh feed. This is something that we cannot avoid, but the goal is to minimize as much as we can the negative effect of the inerts by reducing the concentration as much as possible. So now the dilution of the ethylene and benzene is less than before, and the concentration of inerts is much less. It reduced from 39% to 29%, which is a good improvement in the concentration of the ethylene and benzene. Also, you would notice here that the flow rate in this stream, the flow rate of the stream of the recycle stream is getting much lower. So this 1166 is now 480. So it's less. It's almost 1/3 of the stream. It's a little bit higher than 1/3, but it's 1/3 of the stream. So this is all good news, because we are reducing the load on the uh, recycle stream. There is one other thing which is a very good news actually, that it wasn't meant to be the main goal, but this is also one good result of this, which is the number of moles of inerts in the product is not only here now. So here we had only one exit stream, so this is the only place for the inerts to come out at steady state. But in this case we have two places for the inerts to go. So the concentration of inerts in the product stream was 33%, now it is 24%. Okay, and of course the concentration of ethyl benzene is higher than the concentration of ethyl benzene. So this is good news. Of course, the number of moles of ethyl benzene now is less, of course, because there are some ethyl benzene that are lost here. But this is again what makes the decision at the end, or what decides which scheme that we will go with, is the economics of the process. So this is I might sacrifice some of the ethyl benzene, but this is going to be much more economical than the case without the purging. So, and I hope this point is clear, and why we purge part of the recycle stream, and the goal is to minimize the negative effect of the inerts in the recycle stream. So I'll stop here, and in the next video I'm going to solve one more example about this, which is going to be a very good practice on this idea. So I'll see you then. Goodbye.